Welcome to this explainer. Today, we're unpacking a piece of technology that shows up in practically every system design interview and runs behind the scenes at companies like Twitter, GitHub, and Snapchat. We are talking about Redis. What makes it so fast? Why do teams reach for it over a traditional database? And how does it actually work under the hood? By the end of this video, you'll understand exactly where Redis fits in your architecture and how to reason about its trade-offs. Let's kick things off with Section 1. What Redis actually is. Redis is a single-threaded, in-memory data structure server. That short sentence packs 3 design decisions that explain almost everything about how Redis behaves. First, single-threaded execution. Redis processes commands one at a time in a single thread. Now, Redis 6 and later added I/O threads for networking, but the actual command logic still runs sequentially. This means the order is completely predictable. First request in, first request processed. There are no locks to reason about, no concurrent writes to the same key to worry about. But here's the trade-off. If one command blocks, every other command waits behind it. You might be thinking, if Redis only uses one thread to run commands, how does it stay fast? The answer is batching. Clients can bundle commands using pipelining or wrap a set of commands in a transaction. One network round trip now carries many commands. The single thread still executes each one in order, but the socket stays busy instead of waiting for each request-response pair. Let that sink in. Second, Redis keeps data in RAM. The upside is clear: sub-millisecond latency even under hundreds of commands per second. The downside is durability. If the machine dies, the data in memory is gone, unless we configure persistence carefully. This trade-off is central to how teams deploy Redis. We'll come back to it. Third, Redis is a key value store that exposes data structures directly. A value in Redis isn't just a blob. It can be a string, a list, a hash, a set, a sorted set, or a stream. The protocol itself is small and simple, but Redis provides specialized commands for each data structure. Here's a quick example with a counter. We call setCounter 5. GetCounter returns 5. IncreCounter bumps it atomically to 6. Each command acts on a key, and because Redis runs commands one at a time, that increment completes as a single atomic step. Multiple clients incrementing the same counter won't interfere with each other. Which brings us to Section 2, persistence and durability. Because Redis lives in memory, we need a plan for crashes, and different teams make different choices here. Many teams run Redis as a pure cache with persistence turned off entirely. The database is the source of truth. Writes go to the database. Redis only stores cached results. If Redis crashes in this setup, we lose the cache, but the application rebuilds it on demand by querying the database. No important data is lost because we never treated Redis as the source of truth. Let that sink in. This is the single most important mental model shift for using Redis effectively. Some teams skip persistence but add replicas. The primary node handles all writes. Replicas handle read traffic. If the primary dies, a replica is promoted to replace it. You might lose availability for a few seconds during failover, but you preserve most of the cache data in memory on the replicas. The cost? Each replica roughly doubles your memory footprint. Another option is RDB snapshots. You configure Redis to take a snapshot every few minutes. On restart, Redis loads the snapshot into memory. This lets Redis come back with warm data instead of an empty cache. You accept losing the writes that happened after the last snapshot. For a cache workload, this is usually a reasonable trade-off because the cache warms up quickly anyway. Now, when Redis holds data you cannot afford to lose, you turn on the append-only file. The most common configuration is AOF with append fsync every sec. Redis appends each write to a log on disk. The operating system flushes the buffer to disk roughly once per second. In a crash, you lose at most 1 second of data. You can configure fsync after every command for stronger durability, but that is much slower and has a big impact on throughput. Most teams avoid that unless the dataset is small and latency isn't critical. In practice, the real question is whether Redis should hold critical state at all, or whether it should just be used as a cache. Many teams keep critical data in a durable database and rely on Redis mainly for caching and ephemeral state. Moving into Section 3, Scaling Redis. Most teams start with a single Redis instance. On decent hardware, a single node can handle a massive number of operations per second for many workloads. When reads become the bottleneck, the first scaling step is to add replicas. The primary node accepts all writes. Replicas serve read traffic. This increases read throughput, but write throughput is still capped by the primary. When write volume grows too large for a single instance, many teams adopt client-side sharding. You run multiple independent Redis instances. The application hashes each key and picks a Redis node based on the hash. For a static cluster, a simple modulo hash works. For dynamic scaling, libraries like Katama use consistent hashing so that adding or removing a node doesn't reshuffle all keys. Here's what's critical to understand. Each node is independent. There's no cross-node coordination, no distributed protocol between Redis servers. If you treat Redis as a cache, a node failure simply causes cache misses for the subset of keys on that node until the cache repopulates. Redis cluster also exists as an option. It provides automatic sharding and failover, but this comes with added complexity. Operating and debugging a Redis cluster setup is significantly harder than running independent nodes. Because of this, many teams prefer simple client-side sharding for cache workloads and only adopt Redis cluster when they need its specific guarantees. Moving into Section 4, Real-world workloads. The classic use case is caching. A service checks Redis before hitting the database. Cache hit, return immediately. Cache miss, query the database, store the result in Redis, return the response. Over time, the cache fills up, and you need a cleanup strategy. One approach is setting a TTL on each key. After the TTL expires, the key stops being returned and is cleaned up lazily. Another approach is configuring a memory limit with an eviction policy. Redis evicts keys, typically the least recently used ones, when memory is full. Rate limiting is another powerful pattern. Multiple service instances share counters through Redis, using atomic increment commands on keys representing a user, an IP, or an API token. Combined with TTLs or Lua scripts, you can implement sophisticated rate-limiting algorithms without adding a separate coordination service. And then there are leaderboards. This is where the data structure server part really shines. A sorted set maintains items ordered by score. You insert a player with a score, update a score when it changes, query the top n players, or look up a player's rank. These operations typically run in logarithmic time relative to the size of the set. This pattern generalizes beautifully. Trending post lists, most active users, top sellers, and many other top-N ranking problems all sit on top of sorted sets. Let's wrap this up. Redis is fast, predictable, and versatile. Single-thread execution keeps behavior simple to reason about. In-memory storage delivers sub-millisecond latency. And native data structures, like hashes and sorted sets, solve problems that would be genuinely clunky to implement in a relational database. Most teams start with a single instance, add replicas for read traffic and availability, then use client-side sharding when they need more write throughput. When you understand these trade-offs around execution, persistence, and data structures, Redis fits cleanly into your system designs. Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.